In this video, I will explain how to compute non-bonded force field precursors using the MCLF and Chargemol program. Interaction models are used in molecular dynamics and Monte Carlo simulations of thermodynamic ensembles to compute thermodynamic and transport properties, such as adsorption isotherms, diffusion coefficients, vapor pressures, viscosities, heat capacities, etc. These interaction models can be quantum mechanical or classical. Classical force fields can either be reactive or non-reactive. Reactive force fields handle chemical reactions, which involve breaking and creating bonds. Non-reactive force fields can either be flexible or rigid. For flexible force fields, the energy is the addition of non-bonded terms plus the bonded terms, aka flexibility terms. The energy for the rigid force field is the energy of the non-bonded terms. Non-reactive flexible force fields are made up of non-bonded terms plus the flexibility or bonded terms. Flexibility terms include bond stretch, angle bend, and torsion or out-of-plane parameters. In this video, we are going to focus on the non-bonded interactions, which are van der Waals forces. These include the short-range exchange repulsion, short-range charge penetration, and the long-range dispersion energies. Polarization energy. This can be modeled using atom-in-material polarizabilities. Electrostatic interactions. These can be modeled using a point charge model. Usually, the point charges are located on atomic centers, but one or more off-site point charges are used in special cases, for example, to model the quadruple moment of the N2 molecule. More advanced treatments such as Gaussian or Slater charge distributions or the inclusion of higher-order permanent multiples, for example, atom-centered dipoles or quadruple moments, will not be discussed in depth in this video. To construct a force field, we need force field precursors. The non-bonded force field precursors are obtained from the Chargemol and MCLF programs. Net atomic charges, DDEC6 preferred, because they are optimized to approximately reproduce the electrostatic potential surrounding a material, with good chemical and conformational transferability. Atomic dipoles and quadruples can be found in the net atomic charges.xyz output file in the Chargemol job. They are printed after the computational parameters. In here, we can see the multiples from the 7th to the 15th column. Electron cloud parameters fit the electron density tail of each atom in the material to the exponential decay of function e raised to the a minus br, and they were computed by least squares feet of log of spherical average atomic density equals a minus b times ra over the set of radial values for which the spherical average atomic density is in between 0.0001 and 0.01 electrons per cubic Bohr. Polarizabilities include non-directionally screened, fluctuating, and static-induced polarizabilities, dispersion coefficients, quantum root oscillator parameters, which can be modeled with harmonic spring of frequency omega attached to a pseudo-nucleus of mass m and a pseudo-electron of charge q. The ground state of a specific quantum root oscillator has a specific width which is perturbed if external fields are added, allowing the calculation of polarizability. The energy of dispersion is given by the sum of all orders greater than or equal to 6 of the damped energy. The damped energy is given by the undamped energy multiplied by the time tone's dispersion-damping function, Fn, which is a gamma incomplete function of order n plus 1. The variable s is computed from the derivative of the natural log of the short-range repulsion potential with respect to the distance, Ra, from atom A. The short-range repulsion potential is a function of the electron cloud parameters calculated by Chargemol. The MCLF program first computes the on-screen polarizabilities where dipole-dipole interactions among different atoms are not included. Instead, the polarizabilities are scaled based on the volume and radial moments of the individual atoms. Non-directional screening is then added. In here, the diagonal terms of the dipole-dipole interaction tensor are directionally averaged, so it only includes the isotropic dipole-dipole interactions. That yields the force field polarizability, which is useful to calculate the C8 and C10 dispersion terms. Then, the directional screening accounts for the non-isotropic terms of the dipole-dipole interaction tensor. If dipoles among atoms in a material are lined up, they will amplify each other, resulting in a higher polarizability. On the other hand, if the dipoles among the atoms are perpendicular, they will depress each other, resulting in lower polarizability. When 100% of directional screening is added to the force field polarizability, The result is the static induced polarizability. If instead, directional alignment is present for nearby atoms but lost over large distances, the result is a low-frequency fluctuating polarizability. The latter is then used to calculate the C6 dispersion coefficient. In this 2019 article, the MCLF method was introduced as a set of scaling laws and computational algorithms to better reproduce the properties of the whole material. The MCLF method accurately and efficiently assigns polarizabilities and dispersion coefficients to atoms in a material. Some key advances of the MCLF method include: 1. MCLF has new polarizability and C6 scaling relations for isolated atoms to set the reference values. These cover the charged atoms. Unlike fractional ionic method, MCLF does not require quantum mechanically computed reference polarizabilities and C6 values for isolated charged atoms. Unlike the Takinko-Scheffler TS method, MCLF describes changes in the polarizability to volume ratio with atomic charge state. 2. MCLF uses a new polarizability partition and iterative polarizability screening to improve accuracy and avoid negative polarizabilities. 3. MCLF accurately describes both surface and buried atoms through M-scaling, which provides a unified scaling law describing the different behaviors of isolated atoms and buried atoms. 4. MCLF separates non-directional from directional screening of the dipole interaction tensor. The non-directional screen polarizability is always less than or equal to the conduction limit upper bound, providing improved accuracy for buried atoms. 5. MCLF uses a multivariate screening function to capture the fluctuating dipole alignment at short distances and disorder at long distances, leading to more accurate C6 coefficients. 6. MCLF calculates 3 different types of polarizabilities: the force field, the fluctuating, and the static induced. 7. MCLF parameterizes a QDO model to get higher order polarizabilities and dispersion coefficients. 8. The MCLF atom in material polarizability tensors are always symmetric. 9. Linear scaling, computational cost. This table compares the percentage error in the computed static polarizabilities of 28 solids with different methods. The on-screen methods are inaccurate, as their errors range from almost 300% to around 55%. When using the screen methods, the errors decrease dramatically. However, we can see errors of almost 50% for the TS self-consistent screening with Hirschfeld partitioning, whereas MCLF yields a mean absolute relative error of 12%. In this figure, we can also observe how the absolute error percent for MCLF is significantly lower than other methods for isotropic polarizabilities across different magnitudes of DDEC6 NACS for 57 diatomic molecules. This clearly shows the TS-SES scaling law does not work for atoms carrying a significant partial charge, irrespective of the charge partitioning method. This article introduces the computational aspect of the MCLF method. This figure shows the time and memory required for MCLF analysis scales linearly as the number of atoms in the unit cell increases. In orange, we can see the time in minutes, and in blue, the memory in gigabytes. The required inputs for the MCLF method are DDEC6 NACS, atom in material volumes, R-cubed, R4th, and weighted R4th radial moments. The generated outputs of the MCLF method are polarizabilities, including non-directionally screened, fluctuating, and static induced, dispersion coefficients C6, C8, and C10, and QDO parameters, effective mass, charge, and frequency. The C9 coefficient can be calculated from the QDO parameters. First, a non-periodic system example with cysteine molecule from a DFT calculation. Before you run the MCLF program, you need to run Chargemol through. For more information on how to run Chargemol jobs, please watch our other videos. Transfer the Chargemol results to a new folder in the cluster, and then transfer it to your local computer. Remember to use the text transfer setting. Create a new folder for the MCLF job, and transfer the input files DDEC atom volumes.xyz, DDEC atom R-cubed moments, DDEC atomic R4th moments, DDEC weighted R4th moments, and DDEC6 net atomic charges to the newly created folder, and add the calculation underscore parameters.txt file that can be found in the MCLF source code, and also add a batch file. In the calculation parameters text file, you can choose the settings for the job you want to perform. In brackets at the end are the default values. In this case, we're going to use all defaults. Make sure you have the correct path for the MCLF program in the batch file. Submit the job. check for job completion. Transfer files to your local computer. But first, look for warnings on the dispersion_polarization_output.txt file. Once you know the program terminated correctly, you can analyze the outputs. Let's start with the MCLF atomic polarizabilities for constructing polarizable force fields.xyz file. In here, you will find the number of atoms followed by the xyz coordinates in angstrom, as well as the isotropic force field polarizability for each atom. Such polarizability corresponds to the non-directional screening. Notice the numbers at the beginning of the file are the same as those with description at the bottom of the file. The MCLF C8 dispersion coefficients file contains the xyz coordinates and the C8 coefficients in atomic units. The MCLF C10 dispersion coefficients and QDO parameters file contains the x, y, and z coordinates, C10 coefficients, and the QDO parameters, frequency, mass, and charge. The MCLF low-frequency fluctuating dipole atomic polarizabilities contain the polarizabilities with some directional screening in the last column. The MCLF screen C6 dispersion coefficients has the C6 coefficients in the last column. The MCLF screen static induced atomic polarizabilities file lists the static polarizabilities and the static polarizability tensor. The MCLF on-screen atomic polarizabilities file lists the MCLF on-screen atomic polarizabilities in the last column. The MCLF on-screen C6 dispersion coefficients file lists the MCLF on-screen C6 dispersion coefficient in the last column. The on-screen values are not intended for any real-world use. They are printed because sometimes it is interesting to compare them to the screen values. You can visualize all the files with extension.xyz using Chargemol. Just drag the file you want to view. You could open the console in Chargemol and write labeled %p to show the values of the property analyzed in that output file. In this case, I'm looking at the C8 coefficients for each of the atoms. Note, the numbers of sulfur in the output coincide with the ones shown in Chargemol. Here, I can change the color of the labels to better observe the values. You could repeat this process for as many output files with extension.xyz you want. In this example, we will look at graphene, which is a two-periodic lattice vector material. First, check for no warnings on the Chargemol.output file. Then, place your Chargemol outputs in a folder to transfer to your local computer. And create a separate folder for the MCLF job. Transfer the required inputs along with a batch script and calculation parameters file. Notice we are still using the defaults for the calculation. Now, in BASP, there are three periodic lattice vectors. Because a plane wave basis set requires all directions to have periodic boundary conditions, these three lattice vectors are displayed in the following format on the second line of the XYZ file. The XYZ components of the first lattice vector in angstroms are listed here. The XYZ components of the second lattice vectors in angstroms are listed here. The XYZ components of the third lattice vector in angstroms are listed here. Since graphene only requires two lattice vectors, the third lattice vector in the BASP calculation is made large, 24.6 angstroms in this case, so that the graphene sheets are far enough apart that the atoms from the different sheets have no overlapping electron density. Since dispersion interactions are a long-range force, we need to turn off the extra lattice vector during the MCLF analysis. To get the MCLF program to model a single graphene sheet, the second line of each .xyz input file to the MCLF program needs to be modified to change the last component of the third lattice vector from 24.6 to 0. The lattice vector of 0 length is ignored by Chargemol and the MCLF program. So, by changing the third lattice vector to 0, the system now has only the two lattice vectors within the graphene plane. Save the changes and copy the line. Paste that line to the rest of the .xyz input files and save the changes in each. Submit the job. Check for normal completion. Transfer the files to your local computer. This is an example of 3 periodic lattice vectors of ice crystal with 768 atoms. Transfer the outputs of Chargemol to another folder and to your local computer. Create a folder for the MCLF job. Transfer the input files to the new folder. Add the batch script and the calculation parameters files. Submit the job. Check for normal completion and transfer the files to your local computer. This is an example of how to model a molecule that was computed using a plane wave code like BASP. Recall that BASP uses a plane wave basis set that requires 3 periodic boundary conditions. Therefore, the sulfur hexafluoride molecule was placed inside a large periodic box to enable the BASP calculation. Because the molecule is far enough away from its images that there are no electron density overlaps, the quantities computed by the BASP and Chargemol programs were not affected by the periodic images. Create a folder for the Chargemol results and transfer it to your local computer. Create a folder for the job and transfer the input files. Notice the periodic lattice vectors on the second line of each Chargemol generated .xyz file. Since dispersion is a long-range interaction, we have to turn off the periodic boundary conditions in the MCLF program, so that it's treated as a single isolated molecule with no images. This is done by setting the ignore_pvc variable to true on the second line of the calculation parameters text file. This performs MCLF analysis without any lattice vectors. Submit the job. Check for normal completion and transfer the generated outputs to your local computer. Notice in the second line of each of the MCLF outputs, it says non-periodic system, which proves there were no periodic boundary conditions during the MCLF analysis. This example demonstrates diuranium MCLF analysis for both a spin-polarized material as well as for a system generated using a correlated wave function method, for example, CCSD instead of a DFT method, as well as for a system containing an unusually heavy element. Note, MCLF analysis work for all chemical elements with atomic numbers from 1 to 109. Create a folder for the Chargemol results. Transfer it to your local computer. Create another folder for the new job and transfer the input files. Now, use all defaults in the calculation parameters text file. Since there are no lattice vectors associated with the Chargemol calculation of this material, no lattice vectors or periodic boundary conditions will be present in the MCLF analysis, irrespective of the ignore_PVC value. In this case, it does not matter whether ignore_PVC is set to true or false. Submit the job. Check for normal completion and transfer the files to your local computer. These are the references for the video. For more videos and tutorials, please go to our YouTube channel. We thank the NSF Career Award for making this video possible.